Okay, well, welcome everyone to April's meetup. So just going to get started. We're going to, agenda today is community spotlight. I'm going to talk about some recent releases and a few things that are upcoming, and then deep dive into saving and loading data with Hamilton and the ways you can do that, and specifically talk about data savers and loaders, and which we also ambiguously also use the term materializers for as well. So first up, we have Thierry Jean talking about modular data flows and experiment management for machine learning and evaluation. Thierry, do you want to share your screen? That should be it.
It shouldn't be too difficult since I'm using Google Slides, but we never know. So you can see my screen. Now, can you see? Okay, I have a very narrow view. View tab. Stop sharing. I'll try again. Presenter view. All right. You can see my slides full screen now. Great.
Yep.
All right. So the title is Modular Data Flows and Experiment Management for Machine Learning Evaluation. So I did academic research for 4 years, and most of my time was spent building data pipelines to train ML models for forecasting on time series. One of the main studies we did involved benchmarking 200 plus models, and it's not like 200 architectures, but it was an exhaustive search over a configuration space. I'll detail that later in the talk. And then do some benchmarking, statistical analysis over their performance. And one of the core benefit of Hamilton was having a strong lineage of artifacts and code. So we knew how artifacts were generated. And one unexpected benefit that we had is that in academic research, it's a bit of a cycle between being near your code at your computer, testing new ideas, experimenting, and then going to the drawing board, sketching like your articles, writing grants. And so I would up between the two. And when I would come back to my code, like my Hamilton code would just make sense. Like there were dog strings, type annotations. And since the code is flat with functions, it's easy to extend and refactor when you need to test new ideas. So on the right, it's the main points of the talk. Configuration is basically what you want to try, like your ideas, like your data sets, your model architectures. And the modular data flow is where Hamilton lives. It's a way of expressing this configuration and creating the things that you define in your configs. And then the experiment results. You need a strong and principled way of storing results, because otherwise it's just like dead space on your hard drive and it can quickly fill up. And the different steps are numbered with the order. I'll adjust them. So who am I? Quickly, my name is Thierry. I'm based in Montreal, Quebec, Canada. I speak French, so sometimes I'm searching for my words. And I started using Hamilton in November of 2021. Given it launched in October of the same year, I must be one of the first users. My talk is mostly biased by my enthusiasm for the tool, but just so it's out, I also started working with Stefan and Elijah last year, almost a year now. And I still love the tool, so that's my bias here. And I previously taught ML and data science, did some consulting internship, and also previously did psychometry at an HR tech SaaS company. So creating modular data flows. I'll go through different levels of writing code. I learned a lot over my years of academic research. So this is level 0. It's a single function, a main function. Everything is hard-coded. You see the path to the data file. You see that there's some assumptions about the data frame. I try to have red arrows pointing to the relevant parts, but I hope it will be clear on your screen. So you see that here there are some assumptions about the location X and location Y columns being part of the data set. And there's a bunch of steps that aren't related within the same scope. Step One, like it's already much better. You have functions. So here I have two features. It's the same code as before. You have a location jump, which is the distance between two points, two steps. And then you have the location jump speed, which is the time difference between these two distances. Well, you divide the, the distance by the time. So now it's much clearer. You have the same interface for each feature transform. You pass data frames around, but you have limitations still because the location jump speed depends on the location jump function. Like you see in the transformation that it expects the data frame to have a location jump column. So there's an implicit dependency between features. And the other thing that I want you to take away is that the workflow in main is imperative. You need to be very specific about the order of steps, and you have to manually take care of that. So if you were to change your functions, add or change dependencies, you would need to change the steps found in main each time. Level 2 is checking schemas. I'm also sharing like my journey through like data science, and I created my own check column decorator. It would just wrap the function and make sure that my data frame would have the specified functions, the specified columns. So in this case, like I want the first location jump function to have location X and location Y. And then I could check that location jump speed as the location jump column. This is essentially what Pandora does with check and put. It's much more fancy and like it has a lot of utils, but this is the same idea, like schema checking between functions. But it's still imperative. Like even though I check for things, I need to myself, I have the responsibility of ordering steps and maintaining that, which is prone to breaking once you start to add tens of features. So then I discovered Hamilton around that time, and it made my life much easier. For one, like it forces you to use type hints, which were starting to like be supported in Python. And it makes dependencies explicit. So here, like it's coupled at the function level. I didn't rewrite the function logic, but you get the gist of it. Like the location jump now has dependencies on location X, location Y, as the function parameters. And it makes things much easier in the main function that calls this transform, because now it's no longer imperative. I don't need to define the order of steps because Hamilton knows about the order. I only need to use a declarative approach, which means I ask to get the features at the end of the processing. So here I just pass a list with timestamp, location jump speed, and it will give me back a data frame, given I'm using the pandas data frame result adapter. And also it creates a clear interface between inputs and like the values of the data frame. We see at the bottom that I'm passing the file path for the raw data, which is no longer hard-coded in my functions. All right, so you have your data frame or your data flow with like feature transform or model training, but how do you configure stuff? In my case, like I had a few scripts, and this was my script to train a XGBoost model or like my data flow. You see that there's a bunch of nodes. Like the goal here is not to tell you the decisions between each one, but I circled in red like a few important points. So depending on what type of data set I was using or the model task, I would change these nodes circled in red. And you see that they tend to be like on the left side. And then the bottom, like the right side or like the bottom of the DAG would essentially be the same functions independently of these like top level configurations. Also, you see that the yellow boxes are materializers as indicated on the legend, and we'll come back to that later. So this is just, again, a bit more context about what I was doing. On the left, it's the different dimensions of my experiment. So I was using different forecast horizons for my model. I needed one data set pre-processed for each. Then I was trying two model architectures, essentially XGBoost and like deep learning recurrent neural networks. I was doing 4 learning tasks. So I was doing binary classification, multi-class classification, ordinal regression, and continuous regression. These are very different specs for like the appropriate metrics and the shape of the labels. So this has a lot of impacts on the data flow. Then add 10 target variables, which is they are essentially different columns in the data frame. I would just select them. And add 2 execution mode, one for development, because I don't want to look at my test set before my code is ready for it, and evaluation mode. And the other columns are like the different parts of Hamilton that can handle these configuration, or like where, in my case, it made the most sense to apply configurations. So to change the data set, I just needed to pass a different offset value to the inputs, and it would compute the data set or simply load the data set if it was already computed. To change the target variable, it's again only the inputs. I would just select a different column at the inputs level. For the learning task, it's a much more involved thing. In the execution mode, I needed to change which dataset I would, or like which split of the dataset I was loading. So the driver config was very helpful. This essentially changes which nodes are part of your data flow. But I also leverages modules, which I feel are often not appreciated enough with Hamilton. You can define your workflow in many modules. And so in the previous slide, like here, there's actually 2 modules. One for XGBoost, which is essentially like here on the left. I don't know if you see my pointer, but like on the bottom left side. And everything on the top right side is it's in a separate module. It's one for model evaluation. So if I would switch what's on the left to train now a neural network, the parts on the right for model evaluation would stay the same. So configuration at the driver level is like where it should be. Like all of the things I discussed in the table are here. Like you see, I just passed different modules to the with modules line. I pass config for the mode and the task on the with config, and the rest is inputs. There's a few more points that I didn't mention, but like all of this expressiveness allowed me to train 240 different models, like just that. Like these few lines, like I would pass a config, so the config would exist in a file, or I could do it via the command line, but this is all the expressiveness I needed. And also, I recommend people to break down large data flows into multiple scripts. Like you could have one giant thing with 200 nodes, but if you're to run like prepare dataset, train model, evaluate model at separate times, it makes more sense to break it down. It will be easier to manage. So tackling experiment management. Now I have these 240 like version of the data flow and different models, different types of things I care about. So how do I store that? I tried to work with ML flow and weights and biases. I have, like, I'd say extensive experience with both. And like just to go over why people would adopt them, on the top right, you see like there's direct integration with many ML libraries. I think that's very attractive to people to see like, oh, I can log my PyTorch model, I can log my XGBoost, and it's supported out of the box. It provides a web UI, which is convenient when you have a bunch of like figures, or you have like tables that you want to interact with, and it greatly facilitates collaboration. On the left, you see like the thing you find on the front page of weights and biases. Like it's very simple. Like you have 3 steps and you're done. But from my experience, it's actually much more confusing than that, and like you do spend a lot of time fighting with the framework. For one, like integrations are confusing. I wanted to log the training of my recurrent neural network. Would I do it within PyTorch? Would I do it at the level of Optuna that was optimizing my PyTorch model? Would I do it at the Hamilton level, or like the orchestrator level if I was to run Hamilton within an orchestrator? It gets confusing quickly, and also like you have to opt between the documentation of weights and biases, and then the documentation of XGBoost, and then the documentation of X and Y, and sometimes they're out of date. I'll just say it like that. And the thing that I found weak, and I find it's not addressed by these tools, and they could, is that it's quite hard to find the code that produced the artifact. Like, yes, you have the dashboard, you have like nice visuals, but what part of my code produced that? Like you need to manually seek for it. And there's some weak code artifact versioning. What I mean by that is that I will run my code, it will produce results, but what I will get for weights and biases or MLflow, they will log like the entire Python file, which isn't that useful because it doesn't give me like a clear answer of like as to what version I ran, or it might give me the commit hash. But it's very common in iterative development to change a few lines of code, produce artifacts, but then like these recent changes aren't committed, so they're not related to the most recent commit hash. So I believe things could be made better. But if you are to use MLflow, for instance, you could do it at the node level on the left, but I recommend against it. You see, like this is the function to train like my best model once I figured out the hyperparameters. I have to pass the artifact path and the model name to the function, and I have to add like a few lines to log the model. But this is not part of the data flow. It's not part of the logic of training my best model. There's some coupling that shouldn't be there. What I recommend instead is to log things at the driver level, because it's the person that executes the code that should take care of how things are logged, how they're stored, and it's much more maintainable. So for the same purpose, like on the right, I would execute my data flow, and then I would log the results from the execute statement. One weakness with that, though, is that if there's anything failing in the context of my Hamilton data flow, I will lose all the results and artifacts because it needs to terminate the execute statement. So this is a benefit of the node level logging. So that's why I built the experiment tracker adapter. I see time flies, so I'll try to wrap this up, but this is the good part. This is what we work towards. We created a tracker, and you see it's the same code as before that I used to create my data flows, but I have the experiment tracker statement, which is under with adapters for the driver definition. And it will create a directory with the artifacts I produce, and it will create a repository with the metadata. So now artifacts exist at the Hamilton node level, because when I'm defining my Hamilton nodes like previously, like the best model, like I want to log the best model. I don't want to log like some statement at the middle of the function body. So, and then I needed a clear interface for people to call or specify which thing they want to store. In that case, we already have materializers with Hamilton. So you just pass the materializers in the experiment tracker. It will write the things you care about to a file. In this case, I store like the XGBoost model to the JSON format using an extension we also developed. And it will be available, like it will be linked to the central repository. The nice thing also is that we built a clean and simple UI to view these artifacts locally. And since it's all open source and written in Python, it's easy to extend, which is not the case with tools like MLflow, which are very convoluted, in my opinion, and weights and biases, which is closed source. So quick live demo. This is where I'm crossing my fingers and hoping everything works fine. I will share my code editor. Thank you. I see people crossing their fingers with me on the chat. Right. So this is like the same code I showed before. Well, essentially the same. There's under the Hamilton repo, there's a experiment. You have the examples section, and you have the experiment management example that we added. Once you run it, you will get like this is the cache, the main data that you produce, and your experiments will be stored in like individual runs will be stored here. So it's also easy to like clean space on your disk. And the UI goes like this. I'll just grab the URL. One cool feature with VS Code is that you have a simple browser by default, so you can open it here. And these are my my experiments. The graphics version based on the code and the config I passed. So, for example, all of these version 3 are graphs that add the same config, for instance. And if I click on one, like it's very fast, it's very smooth. You get some info about like the run ID, which corresponds to the things on the left here. You have the graph hash, which is the version of the data flow. And you get your config, your inputs. So for instance, this example takes the inputs and components and n split. We see that this receives a default value of 5, but I passed a value of 10. And this kept the same value as the default value, and no overrides were passed. Then the cool thing is the artifacts. The artifacts read directly from your disk, things that are stored here. And it supports for now like pickle, parquet, and like figures, I believe. So this tells me like my trained model is saved at this location. Then I get the data frame that I can explore. This can have as many columns as you want. It will figure it out for you. And then you have, again, this is a JSON that's also supported, and you can have your plots here too. So that's all for the UI. And the last thing I want to show is I will commit this notebook for the example, but it's very easy to explore your tracked experiment because it's all in a cache that I showed in my file system here. This is the JSON cache. And so I just pass the path. It gives me the path to the name of the run. And then I can load them. And here, for example, I load the image from disk. I load the full like experiment specification, which I can interact with programmatically. And in this case, for example, I load the artifact for the linear regression model that I had pickled. So that's it. Thanks, everyone. If you have like features or things you would like to improve for the experiment manager, like I'm happy to work on it. So just hit me up. Thank you.
Cool. Thanks, Thierry. Anyone have questions for Thierry?
Great. Yeah. I hope it was super clear.
Yeah, no, it was informative. I think, yeah, great for the recording. great. You can also add that. We can clip that part of the recording and put it with the experiment example as well. So cool. So in this section, we're just going to go through some news. So what's new? So we've done a lot, I guess, in the last month or so since we last met. So and thanks to a lot of open source, most of these features are driven by not us core maintainers, but by you, the community. So thanks Swapnil, Fran, Tom, and Wilbur for committing things over the last month. This isn't by no means everything that we put in. This was just mainly like the new features that I picked out of through the release notes. So just to mention just quickly, we do have a lifecycle API. One of the things that we added is a stricter function input and output type checker. And so what this does is it's an adapter that it comes with Hamilton. It's under lifecycle, and you can add it to an adapter. But what it effectively does is that we have the type annotations that Hamilton uses to construct a graph. But at runtime, we actually don't validate by default the values that come out of functions and go into things. And so you see here, Hamilton could build this graph naturally, right? Because B depends on A, and the output of A is a series, right? Hamilton would construct the graph, but when it runs, actually, say someone did something, right? Input.values here is not actually returning a pandas series; it's just returning, an array, right? And so by default, this will just work. But if you include this function input output type checker, we would actually inspect this value and validate that hey, does this meet the the type expected from this function, and then similarly, does this match the type expected for input into B? So just a quick example of like there's a lot more of these hooks that we can add, but so just be on the lookout for them. And they're a lightweight way to kind of not couple your code, not couple your logic, but a way that you can inject things at runtime. The other was a Slack notifier. So thanks to Swapnil for this. This lives under the plugins kind of directory. We have a bunch of plugins there. And effectively, what the Slack notifier will do is that if there's a particular failure in a function, it will, if you set up the Slack notification, it will Slack you an error with the stack trace. So if there's something important for you, you can hook it up to Slack and get notified when it fails. Thanks to Fran, we now have support for providing more finer grained resource kind of options on a per function basis if you're using the Ray graph adapter. What this does is you can now annotate functions specifically for their resource requirements if they're going to be running on Ray. And so this gives you more optionality to have different parts of your graph run on different resources within your Ray cluster. Thanks, Fran, for contributing that. And then we've had kind of on topic of today a lot of things that read and write data, so data savers and loaders. So thanks to Tom and Swapnil and Wilbur for contributing these. So we have a bunch more Polar support. So basically, these are things that are, just wrapping some of the Polar's functionality, but providing a more Hamilton kind of interface around them, for which I'll get into as part of the deep dive in terms of how they're structured and how they operate. But suffice to say, these are, if you're looking for open source contributions, this is an easy way to contribute. But otherwise, I think that's, with Thierry or Elijah, anything else to comment on these guys? I don't think so. But
no, I think like just the materializer that you will explain later are very powerful. Like that's also what I use to store my XGBoost model in my case. And the lifecycle adapter is a very rich and easy to implement API, even if it's not something you want to contribute, but something that's very specific to your use case. You should look into it. That's how I built the experiment tracker hook too. So, yep.
I'm just really excited that all the new changes are coming from users. So I feel like we put in a lot of work to making it like a lower level platform and all sort of these constructs. And now it's just a matter of implementing these constructs. So, right, like Fran, like decorators that can plug into the sort of graph adapter stuff. And then we've got materializers, and each new one of those is a cool new thing you can do. So super excited there. It's really fun. It's a really fun thing to watch.
And then so from documentation examples update, just to pull out a few things. So if you are using parallelism, we did update the parallelism documentation there. So do give us feedback if things could be clearer or you have run into issues. We have more pandas examples. So thanks to Nicolas, he contributed a pandas split apply combine example. Thierry added examples on IBIS. So if you're doing stuff on SQL on top of databases, IBIS is a more Pythonic way to express things that can get compiled down to SQL, and Hamilton complements it. We have DLT, which is the data load tool. This is a new tool that has a lot of hooks or plugins related to saving and loading data off the shelf. They have a very specific scheme, so we're actually looking to have more integrations there. And then Constantine provided integration guides for AWS. So if you're looking to, how can I run some Hamilton code on Lambda or on AWS Glue or AWS SageMaker, we now have better docs and kind of guides there as to how to build a Docker container and kind of push it. And so thanks to Constantine for that. And then, there is now also from LLMs and RAG is hot, and so there's also a new example on how you can set up document chunking with Hamilton that then can run on Ray, Dask, or Spark as well. So find that in the LLM workflows example folder. And then as a fun one, we updated the ChatGPT and DALL-E telephone game to simplify the code a bit that uses Hamilton, and the sister project Burr that we're also kind of created to kind of complement Hamilton. So if you want a little fun thing to look at, you can check out that example. And so one of the big kind of the news is that we've actually we're in the process of open sourcing what we've been building with DAGWorks on top of Hamilton. And so looking at other projects and things, we see Hamilton, they have UIs, Hamilton doesn't. And so one of the things we've been the features that we're planning to open source are things around giving you a more interactive way to visualize things and see your code at the same time. A way to kind of version things. So some of Thierry's code on experiment has provided some guidance here, and then cataloging and seeing executions and telemetry of anything that you run. And so we are looking for a few people from the community who want to kick the tires when it comes out, so we can make sure that the docs work and the things work, but then B, also curious to kind of get feedback. Since there's many directions that we could focus and take the stuff that we're open sourcing. So specifically, one is we'll give you a nice, React a UI where you can kind of more interactively interact with your DAG and understand what relates to what. You'll be able to see when things run, or a catalog. So if you're building feature transforms, you'll be able to create a transform catalog, or if you're creating artifacts as well, track them. And then when things run, see executions, understand successes or failures, right? And then dive into more execution, so be able to compare two different runs. I mean, why do they differ? Or you're trying to debug one. So we're pretty excited with this pretty powerful tool and the various things that we can kind of more easily enable for the OS community. And it comes with lightweight data observability. So this is where if you're really trying to understand and debug something, was it code or data, you should be able to do that pretty easily with the UI that's coming out. With that, that's all the news we had. We obviously have a lot more on the roadmap and a few other things, but just to mention that was, I guess, something that's coming out this month. But otherwise, the deep dive for today is around saving and loading data. You'll hear the term materializers. We kind of, I think, ambiguously kind of use the word materializer to cover both concepts. We do have documentation on this, so if you want to know more under Hamilton, under concepts materialization, there will be another explanation of this, right? And we also do have a bunch of blogs that explain some ideas and concepts for why you might want to do some of the more advanced things that Hamilton enables you to do. So separating I/O from data flow transformations, which Thierry kind of talked about, right? We also, if you're trying to build more enterprise-ready data pipelines, then the separation and platform, usually platform concerns around reading and writing data. And so in which case, what I'm going to show can potentially help you deal with that better. So in terms of just stepping back a bit, the motivation here is every data flow you write with Hamilton, you basically need to feed it data, and then you want to do something with it, right? So you write functions, and then you can organize those functions in modules. But depending on how you approach loading and saving data, you can overly couple to your infrastructure platforms and concerns. So if you're doing something very simple and prototyping, maybe this isn't a concern. That's fine. But if you want your code to live a long, prosperous life, right? If you don't do this well, then you can make your code less portable and potentially less maintainable. So in the example Thierry had before, where you could put ML flow within the body of a function, right? You're now coupled to ML flow, which is fine for a first version, but maybe you don't want that. Maybe you want a platform team to own, or like someone else to horizontally own how you read and write to ML flow. In which case, if everyone embeds how they interact with ML flow now, that code is less portable or reusable potentially. So I'm just going to walk through, the gamut of, or at least how I think about how you can load and save data from a bit of a first principles perspective with Hamilton. And so the one thing to note and watch for is, with Hamilton, there's two ways to execute things, right? And so where Hamilton came from, .execute was the way you did things. But if you're going to be using this kind of the materializers concept, you're going to have to use .materialize for that. And so just to note here that there are two ways to execute things in Hamilton, and in which case that is the one thing to kind of think about or watch for in the examples as to which one do you use when. And so my mental model for Hamilton DAG is, right, you write functions that describe this kind of data flow, right? And then if I want to extend or do something with it, right, it's just a matter of writing a new function and creating a dependency. And so in which case of, say, I have this is a basic machine learning pipeline of taking a digits data frame, creating digits model, then predicting with it, right? If I wanted to save the digits model, like I could save the digits, I could write the code to save the digits model within the function, or I could extend and write a new function, right? That depends on digits model, that then I could save the model if I wanted to. And so just to go through the different approaches of like writing the code that would save this model. Right. One, we could write a function in the DAG, that could do this. And so we could, we would use this potentially with .execute. We could do it outside of the DAG. So this is what Thierry was also advocating for, where outside of the driver, right, you do it. And so in which case, it actually doesn't matter whether you use execute or materialize, kind of up to you. Or you use this kind of materializers concept that I'm going to talk through. And so you can explicitly use a different driver execution method. And then we do have an isomorphic way that you can use it with execute, is if you use the decorator isomorphism with the adapter. So this is where maybe this gets a little confusing. What I'm going to dwell on today is less so about the decorators, because I think we have documentation on that, and more so on the kind of the data savers and loaders that you can use with .materialize. And so, so just go through the first option. As one is you encode something with Hamilton. So if we really want to have something that's conditional, as in meaning like we don't want to save the model every time we run it, but we want the option to, right? We would write a function that depends on digits model and just could be named save model. And so it could look something like this, right? It takes in the model and then takes in any other parameters, and then you can say log to MLflow if you wanted to. And so to run this, right, to get this to run, we would have to, in our .execute, just specify that save model should be run for us to then, save the model. So that's one way that you could, save stuff with Hamilton, or save artifacts from our Hamilton DAG. Option two is you do it outside of Hamilton. So so rather than adding a function here, we actually just tell Hamilton, hey, execute digits model, pass that to me as an output. And then outside of Hamilton, I take the result and then log things to MLflow. So perfectly valid way to kind of do it, right? But the downside of this is that you actually don't necessarily see the dependencies in the DAG of what's happening, but the data flow logic is decoupled, right? It is clean. It is this logic is independent of whether you use MLflow or not. And so this is where the idea came with materializers, is that, well, what if we could actually inject something into the graph? And so that's really where this kind of the design decision, or where this kind of comes from, is can we at runtime actually augment the graph and add nodes to it that will then kind of save things? This is where we use .materialize, and so we have a concept where we can actually specify, hey, we can inject the graph, a node in the graph that says, hey, I want to pickle the result of digits model, and the name of the node here is digits materializers. That's what ID stands for, is notifying here, and then we're passing in whatever relevant information that we need to save it. So in which case here we just need a path, and so. So this means we're not actually augmenting the graph permanently. We are, when we're at runtime, basically augmenting things. So we could have different materializer calls that could pass in different things, but we can also pass in more than one materializer. But just to mention here that this is the way that we kind of can do things now. There is, just to mention, if you want the decorate equivalent, look up save to, and then you can use it with .execute. But this is what we find is the happy medium between, I want to keep my data flow logic independent of how I save things, but I want a more platform and structured way that I can actually add it and then also see it in the graph if I want to. Any questions? All right. And so that's kind of same. So the three approaches, right? And so then what about data loading, right? So very analogously, we have a very similar kind of approach. So one is you could write a function in the graph that loads something. You could do it outside of the graph. So you load it and then you pass it in as inputs, right? Or you can use this, materializers again to actually inject a node into the graph that will kind of do it. And just to mention, there is this approach is isomorphic with the load from kind of decorator. And so specifically, just to walk through those examples, right? So in this particular example, we can load digits df. We can load it from some particular path, right? And so this is one way that we can kind of load data. So this is pretty standard. I want to say this is, if you're doing something for the first version, this is perfectly fine. You could also, if you don't want to couple it within the graph, right, maybe because of dependencies or other things, right, you can actually, load it outside of Hamilton and then pass it in as inputs, right? So in which case, digitdf is now an input to the graph and not something within your logic, right? And so, yeah, you're effectively, materializing things, but again, you lose. So this is nice because things are decoupled, but again, you lose a bit of that, lineage and introspection of how things are actually connected. And so this is where we have you have the ability to then also inject something into the graph. So here there is this kind of from syntax. So we actually can say we have different formats here, right? And so given this particular format, we pass in the right requisite information to kind of load things and say what node we want to target. This will then inject a node into the graph that then will provide as output in this case a data frame which will be named digitdf. If you're using .materialize, just one note that you have to use additional vars to specify something to execute. That is one of the errors or use cases people have run into, is that they specify how to load something, but then don't actually tell Hamilton to compute something. So that is, I guess, the one thing I forgot to mention is that with .materialize, we're not actually specifying anywhere really what should be computed. We're actually implicitly saying what should be computed by providing this kind of this way of injecting the node. By injecting the node, you're implicitly saying, Hamilton, I want to compute digits model and then save it. So that is the one confusing thing potentially that people find with this API is like, okay, how do I specify what should be computed? And so implicitly it's based off of what's passed into materialize, but if it's a loader and not a saver, you need to specify something to be computed if you're not passing in a saver. Question, Fran?
So if you're doing a materialize, can you do an execute as well at the same time, or are they used separately?
So they're pretty isomorphic. So you can use this doesn't augment the graph. So if you take driver and do .execute, it will just run over what you kind of have.
So yeah, additional vars is specifically meant to be like the parameters to execute as well.
Yeah.
So if you do, so what it'll do is the all the materializers, like the from and the to, those will get appended to the graph, and then the right for all the to ones, those will be sort of additional vars, and then additional vars also adds a set of other ones to compute, and it'll return the metadata from the materializers as well as the results of the additional vars. Yeah. So you materialize sort of execute as well.
Actually, so materialize returns a tuple. So one is metadata from the result of these materializers, and then the other part is the result from additional vars. And so materialize is the same as execute if you don't pass any materializers, and instead additional vars maps to the same kind of outputs, and final output vars requested and execute.
And one thing we're thinking about is adding the ability to add materializers in at an earlier stage. So build the driver with materializers as well. Because you could build it with that, and then you could just use execute and say like, oh, this node corresponds to the materializer. So that's something we've been mulling over, still deciding whether that matches the use case.
Does that help clarify, Fran?
Yeah, it does seem a bit odd. Additional vars and outputs. Why is it not called outputs?
Yeah, no, I
think that would be a better name, to be honest, because we have inputs like final vars to match the other one, right?
I want to say, naming things is hard, especially with APIs. And I think one of these, I look at this and I'm like, additional. I mean, like, yeah, like this, we could have named that better. Yes.
Requested nodes. I won't settle down for something.
Well, I mean,
else.
but it's additional, right? So it's like part of it's in addition to what you put into here, and so it's like,
I think the conflict was also that before there was like variables that was a construct within Hamilton, which we moved away from. So
yes.
That's a good question.
Yep. And just to mention, so the alternative, instead of injecting this from, right, we could just annotate it on the function itself. And so this is one way then you could, hide how CSVs are loaded, hide as in, have a more platform way to kind of construct and control it. And so in which case you then wouldn't need to use .materialize. You could just use, .execute here, and you'd get the same kind of graph. So just to look at some code. So I have slides that go out, and so you're able to see all this, but just to kind of run through a few things, right? So I have the kind of the digits example that I have here, right? One way to save things, I could just write a function that extends it and just say pickles it. So that this is one way to save it. But say if I wanted to inject a materializer, right? One of the things I can then do is pass in something to pickle. So I'm not actually running this code here. I'm just showing that if you want to visualize things with materializers, you have to use a different function. It's not display all functions, or it's not just visualize execution. It's visualize materialization. That then can kind of show, hey, we can actually add a new node, model pickler, that will then kind of save things. To your earlier question on execute, so this is where you can use additional vars. So if I also wanted predicted digits to happen, right, I would actually pass it in. When you do .materializer, returns a tuple. So one will be the metadata for the materializers, and the other will then be a dictionary for the results. An example, we could also the isomorphic way to kind of to this is, right, we actually just annotate the function to pickle, right? This gives this is kind of what it does to the graph. Now this means then when I do .execute, I actually just have to add things to be saved. I need to specify in .execute, save .digits model in strings to kind of compute a result. Question, Thierry?
Yeah, I just wanted to point out for the save to .pickle, source and value is also like another construct within Hamilton. That's can get confusing, so I won't explain it now, but like just know that like source can be used within this decorator, and it makes it much more powerful. You don't have to hard code like the path to the here, for instance, you don't have to hard code the save path. You could have source and then pass as in your driver.execute, you can pass it in the inputs, like the place where you want to save stuff.
Yeah, I mean, so just to show the change. So if I do value, means it's an actual kind of string value, right? You'll see here I have a save path as input, but now when I rerun this, you see that save path is gone, because now it's actually hard coded. And so source, what it really is just a shorthand to say, hey, there's either a function or an input that will satisfy this particular value. So you can see here, save path is back again. And so that is something then, powerful concept of, this is one way that you can have materializers or other things. And so with dependencies here as well, right, you can have it depend on any number of things in the graph, and then have things going to be passed in to that particular materializer. Loading data, just to show the analogous kind of code again. We have digits.df that does our loading here. Here it's kind of internal, right? But like you kind of see that here. One thing that we could do is we could actually replace. So the thing with materializers is that we can also kind of override. It kind of automatically overrides this particular function. So one of the things we can kind of do here is actually we want to load digits.df from a particular CSV. So one way that people potentially use materializers is kind of caching or a way of kind of using it in that sort of a vein. So if you've computed something, you can just inject something into the graph. So this is another way. Instead of using overrides equals, you can use this kind of from syntax to override this particular function and instead inject the output or the result of this into the graph. Powerful stuff. And so then the isomorphism to the decorator, right, is you could use this load from syntax, and again this is kind of what it will kind of unroll things into. But again, you can use the source values. You can have different inputs to have it depend on different things. But this is one way that you can kind of hide. Use the adapters and then use dot execute without using dot materialize. So that's basically kind of top level mechanics in terms of like what is how does what do I have to implement to kind of construct my own from or to, right? And so I want to say it's a very simple interface. So we have a concept of a data saver and a data loader, right? And you can see here I have created a custom implementation for scaling. That's just doing some basic stuff to pickle something. You can see here that we're using data classes, right? And that's just to kind of make the class shorter. You have to deal with a constructor, and so one of the internal values is path. This could be other parameters could go here that we would then have to pass in or satisfy when we construct this particular object. But the two class methods it has to implement is to say what types it's applicable to. So in this case, I am specifically saying it's only applicable for SVMs, and the name of this is pickle, right? And so this is the value here is really what determines what comes after from or to. So in this case, it is a saver, so it will be the to. So if it will be to.pickle, but if I had my own custom implementation, I could do to pickle, custom, and then in which case this would mean I would do pickle underscore custom, and then pass in the things. And so that's how we'd kind of dynamically do some mapping on the back end to map name to kind of this particular attribute. And then the only other function you need to implement is save. And so save takes in the type that you kind of expect. It has to return some sort of metadata, so that's why we return a dictionary. But you could do whatever you want on the internals of this function call using whatever values or parameters configuration that you've passed in. So pretty short. And the only other thing you need to add then is just to register it. And so there is a Hamilton registry that you just need to register adapter so that when you import this module, it will register with Hamilton, then Hamilton will know about it. Question, Thierry?
Yeah, these classes are actually pretty quick to write once you get the concept. Maybe one way to frame it is that you're defining a class that's the skeleton for creating a function, like a Hamilton function or an Hamilton node. So the applicable type would be like the type it receives. In that case, since it's a loader, it would be like the type annotation of the data object it receives. The save data would be the body of the function.
Yeah.
And the name here is a bit like special. It's like the name you give to the decorator or materializer.
Yeah.
And it will be the same for the loader, where the type will be like the return type of a function, the name, and the body of the function.
Yeah. So then to kind of use function custom, right? Or we just need to have make sure that it's imported. So this by default is running. It's imported because it's running in a notebook. But if this was in some sort of module, right? This is like my adapters.py, right? You would, before using it, just have to import my adapters such that it actually registers itself with Hamilton.
Being the register function we need to call. So
Yep.
if you have the init file and you import it, you could also just call it init.
Yep.
Or like the init function or something.
Yeah, but otherwise, not too different. But effectively, this is one way that you can do things, right? And then similarly on the creating custom loader, pretty analogous, right? You might use a loader, for example, to check different databases or schema types or other things on how things are loaded, maybe even ACLs or something, right? And so You can use some sort of post init stuff so that we can check or create a connection, or you can do something fancy. But as Thierry was saying, the applicable types here is specifying kind of what can this loader proceed. So it will output a data frame, and only functions that are, or inputs or fields that are inputted, annotated with a data frame can be connected to this particular data loader. And you can kind of see here, name could be, whatever we want, proddb, and this will be then from _.proddb is kind of what we're declaring here in terms of functionality. The from a loader though, the two things, it actually returns a tuple. So one is the type or actual value that it is, and then some metadata around it. Now, the reason why we want metadata around these two things is that then this can feed into something like tracking and understanding, what was read to and saved from. And so this is where, we're building capabilities, for example, to, use this metadata information to, emit open lineage or, know that an artifact was generated or saved, right? And so that's kind of the reason to kind of have metadata returned with each one of these save or load functions. But yeah, that's the rough mechanics of the more advanced side of how do you implement and do stuff with saving loading data with Hamilton. In terms of just to show you a real implementation, right? So under plugins, you'll see a bunch of extensions files. So this is where a lot of these materializers live, and so. At the top, we generally have some type guard checking, or so import checking to ensure that you have the right dependency, right? But otherwise, you can see here that the one for pandas CSV, we actually, there's a lot of extra parameters exposed because this maps to what you can actually pass into pandas, read CSV. You can see the applicable type here is data frame. So most of these extensions map to a particular type. And so in this case, it's just a pandas data frame. We, checking the different kind of keyword arguments, and then, wrapping this in a call and providing metadata. So not too complex. And so if there are things or common tools you use, implementing and contributing one back is, I want to say relatively straightforward. Question, Thierry?
Yes, one I was very excited about is implementing a matplotlib file saver because I never can remember the API. So now I just return a figure, matplotlib figure object, and it saves to PNG or SVG or whatever I specify. So
nice. And I think you can find that under matplotlib extension. So you can see there's a matplotlib writer. Cool. And so we don't have an ML flow one contributed, but we do have a sketch of one, and so we're actually looking for feedback as to what would make sense here. But just to mention, if you are looking at ML flow and you want one, I have one that you can start with, and would love feedback as to what should be contributed actually back, since there's a few ways that you can use ML flow, and so that's the main reason why we haven't pushed this back. But link here in the slides. So to recap, basically there's three main approaches. So you embed with Hamilton, you do it outside with Hamilton, or you use kind of these materializer data saver loader constructs and inject it into the graph. But so there isn't one right answer as to which is the best way, right? We have this kind of, we can allow all approaches, but I think with the modularity and everything we encapsulate in functions, it actually allows you to progress and swap things out over time more easily than you would with other frameworks. And so then you have your choice of how much do you want to couple, and actually with all these approaches you can actually mix and match. In the docs there is a side-by-side comparison in terms of if you want to kind of see and understand a few of the different ways, right? So check that part out. And otherwise we have a few more blogs and other things that will show you more applications of using the data savers and data loaders. And so in terms of in terms of, if you go down the route of looking at data servers and loaders, right? And so where we've seen the most benefit or the most people who uptake them is people who, want more of a platform approach to kind of encapsulating and centralizing how things are written. And so the idea is that, if you want to centralize how things are read and write, if everyone does it in their own function, well, you're going to have 15 different ways for 15 different people. But if you standardize on an adapter, right, then you have then you can kind of centralize that, and therefore incur less tech debt, and then have simpler migrations. I think one of the interesting parts of using the .materialize for saving things is really actually easy to implement a dual writing scheme. So commonly there's, if you want to change formats or other things, there's a whole process to kind of do so. But in the case of Hamilton, you can have more than one materializer for the same object, right? And so you can actually inject multiple different ways of saving something, and then, have a smooth path to migrating things. And then otherwise, with the extra metadata that you capture and control, right, you can actually log more stuff about it. So this is where I was saying that with these materializers for saving loading can do more things within them. So they could, ping an internal service. They could, have metadata, and then you can expose and track, right? And so coupled, say, with a lifecycle hook, there's a lot of flexibility and functionality that you can kind of input and build together. So in terms of next month, so I'm still deciding on a date for the meetup next month. Part of the challenges is that we're going to be at PyCon. It's about a startup pro, so a lot more people are going to find out about Hamilton next month. But if you're interested, we are looking for community spotlight corner to help cement a particular date. But otherwise, if there's questions, thoughts, concerns, happy to stop recording. But otherwise, thanks everyone for showing up. And for those of you who are tuning in, thanks for watching.
Live idea, Stefan, a in-person meetup at PyCon in Pittsburgh. Take people out to drinks and talk about Hamilton.
Yeah, I mean, if there's people going to be in Pittsburgh for PyCon, yeah, definitely. I guess that's something, we can announce.